Hello! We are now in the very last section of this chapter. So, and you know how it goes. Every chapter it seems like we learn a new method or something new. And then at the end of the chapter we talk about how do you use these in applications. So you probably knew this was coming. But the good thing is one of the applications is sort of new. But all it is a new formula kind of. So you'll get the hang of it. But the other type of problem is just a problem we've seen before. Actually, I think it was chapter 1, if I remember right, or it was quite a ways back, but it was applications where you're talking about distance, rate, and time. And if you remember, you have to make a little table of values and all this type of stuff. So it'll be a review of that, distance, rate, and time. And then an introduction into just one new type of problem, which really all you need is a formula for. So it's not really too bad. And then in the last section we learned how to solve rational equations. So once we set up the equation, it should be fine. It'll be like more of the easier problems from the previous section, because we saw some pretty tough ones. When we set these up, they won't be as tough as a lot of those. So let's see, the first type of problem we're talking about here, the work principle. So really, just to give you an introduction, this has to do with, let's say two people are doing a job. Like, baking a cake, let's say. I don't know. It doesn't have to be a boring job, right? Baking a cake's fun. So, like, let's say if the first person 1, can bake a cake in 5 hours, I don't know. And then person 2, they can bake a cake in 4 hours. By themselves. So one person takes 5 hours alone. The other person takes 4 hours alone. What if you'd like to know, well, what if they worked together? How long would it have taken them? Probably less time, right? So that's what the work principle is talking about. If two people or things are working together, it's going to take less time than if they worked separately. But you might want to know how long exactly it's going to take, So it's kind of interesting, and there's a formula for it here. But let's see, what are all the parts of this formula? This says, the work principle. If A, lowercase a, is the time needed for A, capital A, to complete the work alone. So think of A as like person 1, I guess. Usually it's a person, but sometimes it's like, I think I've seen examples where it's pipes, like let's say there are 2 pipes or hoses that are filling a swimming pool. And let's say it says, the larger hose can fill the pool in 3 hours, the smaller hose can fill the pool in 5 hours. What if you use both pools at the same time, both hoses at the same time, so that the hoses are working together? How long would it take? So it doesn't necessarily have to be people. A lot of times it is people, but it could be just whatever's working together, like something that's filling a pool like that, or a person. Anyway, so think of capital A as a person, or an object, I guess, that's doing some kind of job. So lowercase a, it's the time needed for the first person to complete the work alone. And then similarly, lowercase b is the time needed for capital B. Let's think of that as person 2. To complete the work alone. So I guess it's kind of confusing because lowercase a, lowercase b, those are times. Keep that in mind. A is time and b is time. It's kind of like the individual times of the people that would work together. And then the last thing, lowercase t, that's the time that it would be needed for both of them to work together. So you think that little t, lowercase t, should be a smaller number than lowercase a or lowercase b. And that's because it should take 2 people less time to work together than it does for one of them to work alone. So you can always expect lowercase t to be smaller than both a and b. And a and b one could be larger or smaller than the other. It doesn't really matter. But anyway, if you have that situation where 2 people or 2 things are working together, then this would be the equation that models all that time. So notice it's 2 rational expressions, lowercase t over lowercase a. That's the time needed to work together over the time needed for person 1 by himself, plus the next rational expression is lowercase t over lowercase b, where then, again, that means the time needed to work together over the time for person 2 to work alone. When you add those 2 rational expressions together, you should get 1. So that's the equation we'll be using in these problems for the work problems. So right now in example 1, part A and part B, I'm just going to get ready for that. I know that these problems are both talking about work, so I'm just going to place this formula getting ready for it on both of these, and then I'll try to figure out what each of these items is depending on the problem. So let's see, I'm going to read through part A just really carefully and try to identify T, A, and B. And of course, one or more of those things might be something that I don't know, and I'll have to leave it as a variable, because that's probably what I'll be solving for. Okay, so it says it takes Kelly 10 hours per week to prepare food for delivery for senior citizens. Okay, so it sounds like Kelly's working alone. That probably means that 10 hours is like lowercase a. I guess if you're thinking of Kelly as person A, you know, the first person, then lowercase a would be 10 hours, the time it takes for that person to work alone. Okay, so we know lowercase a. And then it says, the next sentence, Natalie can do the same job in 15 hours. Okay, so I think we're thinking of Natalie as person B. That means 15 hours, that's probably lowercase b. So that's how long it takes Natalie to work alone. Okay, and they want to know how long would it take for the two of them to prepare the food working together. So it sounds like what they're looking for is t. Because remember, t, the lowercase t is how long it takes them to work together. So since that's something I don't know, I'm going to expect to use this formula but not replace t with anything, since that's not what I know. But I can replace a. They said in the very beginning sentence, a was 10 because it took Kelly 10 hours. In the second sentence, it said it took Natalie 15 hours. So at least I can fill those in for a and b. It's just that t is something I won't know. Alright, now that's pretty much it. Now I can solve this equation, because now there's only one variable left to solve for. So we know by now you can solve any equation that has one variable. It's just when it has two or more variables we can't solve it. That's why the formula itself something had to be filled in there, because we have three variables, t, a, and b. I got to figure out what kind of information I can put in there so that I only have one variable. But thankfully we kind of figured it out. So now we have t over 10 plus t over 15 equals 1. So I'm going to use the method that we learned from the last section and say, alright, I think I'm going to multiply the whole thing by the least common denominator to cancel denominators. And I think looking at these two denominators, 10 and 15, the LCD would be 30, since that's the smallest number that both 10 and 15 divide into. So I'm taking the whole thing, multiplying it by 30. Each fraction and the one on the other side. Every term gets 30 multiplied by it. Sounds good. So it'll be 30 times the first fraction, t over 10, plus 30 times the second fraction, t over 15, equals 30 times the 1 on the other side. I'm just going to say that's 30. 30 times 1 is 30. Alright, now let's put those 30s on the left side over 1 so I can see what reduces here. In the left product, I can see that 10 can go into 30 3 times. So this whole first term will just become 3 times t, which is 3t. The second product here, we have the 15 going into the 30 twice. So you'll be left with 2t for that term. And on the right side, it was already very simple. It's just equals 30. And it's amazing how simple these problems get once you kind of do a few steps. It's really as simple as it looks. You have 3t plus 2t. Those combine to make 5t. 5t equals 30. And I will solve it by dividing by 5. And that'll be it. So it looks like t is 6, huh? 30 divided by 5. I should make sure that that's what they asked for. Because remember, t stood for how long it takes them to work together. Is that what they asked for? How long would it take for the two of them to prepare the food working together? Yeah? Okay. That's what they were asking for. But maybe I should probably write this in a complete sentence. So someone reading this would say, okay, what the heck is 6? What am I going to do with that? I'm going to say, okay, it would take Kelly and Natalie 6, and I think the type of time they were talking about was hours, right? They weren't talking about, above they talked about 10 and 15, but those were measured in hours. So I think the time is always measured in hours in this problem anyway. But if it was 10 and 15 minutes, it would be, my answer would be 6 minutes. But it would take Kelly and Natalie 6 hours to, I don't know. There's a lot of ways you could phrase this. To complete the task when they work together. Alright, so that definitely cut down on their time, right? It took one of them 10 hours alone, it took the other one 15 hours alone. But together it only takes them 6 hours. That's pretty good. Alright, so that's the idea. We'll see in this next example. It can get a little more complicated, but it's still not too bad. You're just kind of, as long as you're careful and you think about, as long as you remember what T and A and B stand for. T is how long it would take them to work together. A and B are how long it would take them individually to work alone. Okay. Let's read part B here. Tristan, he's an experienced programmer. He can write video game software 3 times as fast as Sarah, who is just learning the program. Okay, fair enough. Working together on one project, it took them 1 month to complete the job. Okay, that's a number. I can do something with that. Said, okay, working together, that means that this number must be lowercase t. T is 1 month, because remember, working together is t. Working alone would be A or B. Well, I know lowercase t. I guess I don't know A or B, though. How long would it take each of them to complete the project alone? So I guess what we're looking for is A and B, because that's how long it takes each of them to work alone. I guess we'll say A is how long it took the first guy, Tristan. Tristan's time alone, I guess I should say. And then B would be Sarah's time alone. Alright, so first I'd probably just fill in what I know. They only gave me one number. Let me see how that looks when I plug it in. Those formulas, T over A plus T over B is 1. But I only know T, I don't know A or B. T is 1. But there's 2 places for T, so I'm going to put a 1 for both of them. This is where I say, uh-oh, I think I need to do more or I can't solve this equation because I still have 2 variables. If it was all A's or all B's, I would be able to solve this. So there must be some other clue in there that would allow me to have an equation with just one variable or the other. So what kind of information have we not used yet? Let me read it again. It says, Tristan, an experienced programmer, can write video game software, I think this is it, 3 times as fast as Sarah. Okay, so let me see. I'm going to say, let's say Tristan, how long he works, that was A, right? We kind of said that over here. A is how long Tristan works, and then I guess then that means that Sarah's time would be B. Okay, but they said, okay, I'm going to kind of write this down. It said, Tristan's time is 3 times as fast as Sarah's times. Okay. But I think that's almost misleading because it makes it seem like, well, does that mean that A, Tristan's time, is 3 times Sarah's time? Because remember we said up here, A is Tristan's time and B is Sarah's time. But I don't think that would make sense because he's working 3 times faster. So I guess what that means is Sarah's working 3 times longer. Because remember, A and B, they don't represent how fast you're working. It's not the speed. It's how long it's taking. You know, how many hours. So I think what I need to do is kind of translate that into time. Because that statement, the red statement we just wrote, Tristan's time is 3 times as fast as Sarah's time. That's more like his speed, how fast he's working. That means, in other words, that means Sarah is going to take 3 times as long as he will. Yeah, because if I had written that his time is 3 times Sarah's time, that wouldn't make sense. That would mean he's taking longer than her. So really, even though they said Tristan's time is 3 times as fast as hers, that really means the amount of hours she's spending is 3 times what he's spending. So I guess the equation we're coming up with is Sarah's time is 3 times as long as Tristan's time. Remember, this was Sarah's time. Time B is 3 times as long as Tristan's time. That's kind of tricky, but we did come up with a relationship. So I think in this equation over here, 1 over A plus 1 over B equals 1, I'm going to replace B with 3 over A. Kind of like we're substituting, you know, using the substitution method. Substitute B equals 3A. So I'm going to leave everything else the same. It's 1 over A plus 1 over B, but again, I'm replacing B with 3A. Because Sarah took 3 times as long as Tristan. So this one was tricky because the way they wrote it sounds like sounds like Tristan, his time is 3 times as long as hers, but really he's working 3 times as fast, which really means that his time is less, you know. So she's working 3 times as many hours as he is, since his speed is 3 times what hers is. Alright, now we finally have an equation that has one variable in it. This just has an A in it, that's it. Now I'm able to solve it by finding the least common denominator and multiplying the whole thing by it. So looking at those two denominators, I noticed their LCD would be 3A. using methods that we learned before. So 3a times that, I'm going to need to multiply that by all three of these terms, the 1 over a, the 1 over 3a, and the 1. Okay. Let's see. So I'm going to, just to be safe, you don't have to do this if you can see what cancels like we talked about before. This step is kind of not necessary if you can see what cancels. You can skip this step. But I'm first multiplying 3a by 1 over a, then 3a by 1 over 3a, oops, and then 3a times 1. Alright, let me fill those in there. We got 3a times 1 over a, okay. But also 3a is being multiplied by 1 over 3a. And then it's also lastly being distributed onto the 1, 3a times 1. You could have just written 3a right there, but that's okay. I'm going to put each of these 3a's over 1 so I can see what reduces. The a cancels on the first one, so you're left with the 3 times the 1, which is 3. Plus, in the second one, you see that 3 and a both cancel, so it's really just a 1 left there. Plus 1 equals 3a times 1 is 3a. There we go. And then on the right side, you see that there are like terms, 3 and 1. You can add those together. That's going to make 4 equals 3a. Alright, now we can solve it by dividing by 3. And that should be good. A is 4/3. And this is where I forget what A stood for, but above I wrote that that's Tristan's time. 4/3 of an hour for Tristan. And I'm going to make sure that's all if that's all they asked for, then I'm done. But if they ask for more, I better do more. The question was, how long would it take each of them to complete the project alone? Okay, so I found how long it took Tristan to complete the project, but not, what's her name? Sarah. That one girl, Sarah. But remember, we had this relationship up here. We just wrote it up here in this red box. Sarah's time, B, is equal to 3 times Tristan's time. So I can figure it out by just substituting the value of A I found for Tristan. Tristan took 4/3 of an hour. I would put that over here. Just substitute that guy in there and multiply. And if I put the 3 over 1, I notice the 3 cancels with the 3, and you just get a 4 in the end. 4, okay, so it must have taken 4 hours for Sarah. Alright. And of course, they want you to write that in a complete sentence, so I'd probably say something like, it would take Tristan 4/3 hours, and Sarah would take 4 hours. Alright, but I think if you mix those up, if you were worried, wait, I don't know if I would have put B equals 3a, I think I would have accidentally put A equals 3b. But when you're done solving, you would have realized that I think you'd get the same answer, it's just Tristan's number and Sarah's number would be opposites. So you would have found that Tristan took 4 hours and Sarah took 4/3 hours. But then you'd realize, wait a second, that can't be right because he's supposed to be faster than her. How could he have more time? How could it take him more time than it would take her? And then that's when you'd realize something's probably wrong. Maybe I switched the two. So anyway, don't worry. If you're worried that you would write A equals 3b instead of B equals 3a, then that's not a big deal. It'll kind of correct itself once you kind of use logic in the end. But I think ours makes sense because Sarah's supposed to take a while since she's new. 4 hours. It takes him 4/3 of an hour. And another way to think of that is that's 1 1/3 hours. Because remember, 3 goes into 4 once with 1 left over. That makes sense. 4 hours, 1 1/3 hours. It does seem like he's going 3 times as fast as her. So that sounds about right, I think. Whew. Alright, those problems are tricky. And it's not really solving the equation that's tricky, right? It's more setting it up. So trying to translate the words that they give you into, the equation and knowing how to fill in T and A and B. But the good news is, at this point, we're going on to the other subject in this section, which is something we've seen before. We've seen distance, rate, time already. So it should be, not too crazy. It'll just be kind of a review, and then the only new thing is once we set up the equations, we'll see that they'll be the rational type that we just learned how to solve in the previous section. Okay, so we kind of reviews how to go about these. So recall that these distance, rate, time, D equals RT is the formula we're going to use. Recall that that's true and that it is the best to solve these problems by following these steps. First step is you're going to fill in the given quantities D, R, or T into the table. Because if you remember, in every example, they either give you both distances outright, or they give you both rates outright, or they give you both times outright. They're just given to you, no questions asked. I would fill those in right away. So that's step 1. And then step 2, now that you've filled those in, they should give you, maybe they won't give you one of the remaining things, both distances, both rates, or both times, but there should be one of those where you know a relationship between them. Like if they said, oh, on the first part of the trip, I drove 10 miles an hour faster, then probably mean that one rate is 10 more than the other or something, and you can fill in maybe x for one and x plus 10 for the other. Just some kind of relationship between them that was given. Alright, then we do that. Then that means at this point, after step 1 and step 2, 2 of these columns should be filled in and one maybe is blank. So the third step is you're going to use this formula D equals RT to fill in the final column. And then everything should be filled in and you're ready to start an equation. So step 4 says there should be a relationship between the final entries that you just filled, whatever they were. You're going to form an equation by that. So we've seen these steps before in a previous section. It's just, now the equation we get when we set it up is going to be more complicated. So alright, let's look at example 2 here. So part A, it says a loaded roadway truck is moving 40 miles an hour faster than a New York railway freight train. In the time that it takes the train to travel 150 miles, the truck travels 350 miles. Find their speeds. Alright, so as it says, you're going to want to make a table in all these problems for sure. So okay, I'm going to make it, you want a column for each of the distance, rate, and time. So I'm going to have one for T, one for R, one for D, and then the very left one should be for, the parts of the trip. And it depends on the problem. Like, up in the kind of example here, it says part 1 of trip, part 2 of trip. I'd probably make it more, more specific to the problem. Like here, I think the things they're comparing are this roadway truck and then this railway's freight train. I'm going to label them as one is a truck and one is a train, That's what it seems like we're talking about here. Truck versus train. Or train versus truck. It doesn't matter what order you put them in. So I'd make it the part 1 of the trip, part 2 of the trip, make it specific to your problem. Alright, now that we have the table set up, like step 1 says, I want to fill in, one of the things is given. Do they give me both distances? Do they give me both rates? Or do they give me both times? If I read it again, okay, the roadway truck, it's moving 40 miles an hour faster than the freight train. That doesn't really give me what either of them are. I don't really know their speeds. I just know that one of them is 40 faster than the other. So it doesn't really tell me anything. I think I'll use that later. Let me keep reading. And the time that it takes the train to travel 150 miles, there you go. So that's already giving you the distance. So that's the train, right? The train traveled 150 miles. I'm going to put that where under distance next to time. Or sorry, next to train. Under distance next to train. Then it says the truck travels 350 miles. Okay, so that means that the distance for truck is 350. Alright, we got step 1 down. We filled in something that they just gave us. And then step 2 says they should give you some kind of relationship between either variable that's left over, the R or the T. And I think the very first sentence gave that to us. They said the truck is moving 40 miles an hour faster than the train. So I think, let's say that the train was moving, X miles an hour, Let's say X is the speed or rate of the train. Okay, then if the truck's, I guess the truck now, you want to look at that, the speed of the truck, he's going 40 miles an hour faster. That would mean his speed is the same as the train, whatever it is, X, plus 40, because it's faster. So I think that'll help me fill in the rate. Remember, rate is the same thing as speed. It's just a different way to say it. Alright, so if the train was going X miles an hour, the truck's going 40 miles an hour faster, which is X plus 40. Whew! Okay, we got step 2 down. Now step 3, it says, using the formula distance equals rate times time. So I'm going to have to write that guy down real quick. You're going to fill in the final column. So for us, this is where we haven't seen this before. This is kind of a new thing. Because T is what's left over, I need to find T. That means I'm going to solve this equation for T, get T by itself. So that's pretty much what you have to do. Take distance equals rate times time, this formula, get the variable by itself that you need, the one you're missing. Okay, D equals RT. Let me see that guy. Well, if I want to isolate T, it's being multiplied by R. To get rid of R, I'll do the opposite and divide. And that way t is by itself. T is equal to distance over rate. Alright, and that's how I'll fill in each of the times. So this time up here for the truck, it'll be the distance of the truck, which is 350, over the rate, which is x plus 40. And then for the train, I'll do the same thing. I'm going to take his distance, which was 150, put it over the rate, which is x, according to this formula. So the train and the truck, it doesn't matter which one you're talking about, its time is its distance. So this guy's 350 over its rate, which was x plus 40. Alright, and then the same thing for the train. His distance is 150, his rate is x, so it's distance over rate. Just remember, you're using the formula there to set that up. That's distance over rate, this is distance over rate. Okay, there we go. It looks a little messy there, sorry. Whew. Okay. Ah, wake up. There we go. That's distance over rate, that's distance over rate. Okay, and then we got those, we use that formula to get there. Whew, alright, we've done steps. How many steps is that? 1, 2, 3? Let's see, where was that step? Step 3? Yeah, okay, step 3 said use that to fill in the final column. Alright, we got it. And then as it says, there should be some kind of either a outright spoken relationship between the things you just filled in, or it should be kind of secret, not secret, but unspoken relationship. But now at the last step, or step 4, I'm going to get my equation by asking myself, is there some kind of relationship between the times? Because time is the last thing I filled in. Let me see, I'm going to write that down before I forget. Relationship between the times. And if it happened to be that the rate is the last thing you filled in, at this point you'd be looking for a relationship between the rates. If it was distance was the last thing you filled in, you'd be looking for a relationship between the distance. Okay, but let me see. They said loaded railway truck is 40 miles an hour faster. Okay, that has nothing to do with the times. That's the rates, so that's not going to help. Okay, but then notice in the second sentence, right off the bat, they say, in the time that it takes the train to travel blah blah blah, the truck travels blah blah blah. So I think those 3 words, in the time, that implies the times are equal. Yeah, they said in the time. So basically they're saying, when one of them travels 150 miles, the other one travels 350 miles in the same amount of time. Same time. So pretty much, if I want to brainstorm, it's the time for the train is equal to the time for the truck. In this situation anyway, since we're talking about the truck driving 350 miles, the train driving 150 miles. So I'm going to take the times from the formula and fill them in this little idea here. So time for the train, according to the table I have up there, the train took 150 over x. That was the amount of time it took. That should be equal to, okay, the time for the truck, that was up here in the table, 350 over x plus 40. Whew, there we go. Now there's our equation. Okay. I think we can solve this guy. So now that we've set it up, that was the hard part. The easier part is now just trying to go back to the previous section and think, how do I solve these guys again? Okay, first thing I want to do is see what the LCD is and multiply the whole thing by the LCD, this whole thing. But I noticed the first fraction has a denominator of x. That doesn't factor, so that's kind of its own factor. I'll need that in my LCD. Same kind of thing with the second denominator. X plus 40 doesn't factor, so it's kind of its own factor. I need that in my LCD as well. So really it's both of those put together as the LCD. And I'll need to multiply, there are only 2 terms here, one on each side. But I'll need to multiply both of them by this common denominator. Alright, I'm going to distribute it onto both. X times x plus 40 times the fraction on the left, 150 over x, equals, okay, now that same thing, x times x plus 40 times the fraction on the right, which was 350 over x plus 40. Alright, now we're going to see what reduces here. Let me put the left thing over 1, and notice the x's cancel on the diagonal. So what's left is the 150 that was already in the numerator, times the x plus 40 that's left over from the LCD. And remember we said that you could write x plus 40 on the left and then 150 on the right, but it's just easier to distribute from the left side, I think. So I always write the constant term that's going to be distributed and then the kind of the binomial or the trinomial or whatever it is on the right side. All right, that'll be equal to, let me put this guy over 1 as well. The x plus 40's cancel on the diagonal, but the 350 that was left in the numerator is there, plus the x that was part of the LCD. There we go. Okay, I think we're getting there. Now I'm going to distribute that 150 in. 150 times x was 150x. 150 times 40, let's see. Well, 150 times 4 is 600, but 150 times 40 would be 6,000. Ooh, that's a big number. And there's not really much to do on the right side here. I'll just leave it the same. And now I see that there's no x squared term, it's just an x. So I'm going to be able to just isolate x by maybe moving the x's together by subtracting the 150 to the right side. That way 6,000's all by himself on the left. On the right, let's see, 350x minus 150x is 200x. And I'll divide both sides by 200, and that should be x. Alright, let's see, what's that guy? That'd be 30? Is that true? Yeah. Oh no, yeah, 30. Alright, now at this point, I don't know about you, but I always forget what I was doing. I'm like, what was x? What problem am I even doing? Where am I? Am I doing math? I don't even know. What did x stand for? If you're looking for what x stood for, you got to go back to the table you drew. Where did I put x? He was right here in this kind of middle part, and he was underneath rate, so it must be rate or speed of, okay, he was next to train, so that must be the speed of the train. Okay, let me see, I'm going to write that down before I forget. The speed of the train. And let me go back and see if that's all they were asking for, then I'm done, but if they want more, I might need to do more. What'd they say? It said find their speeds, plural. Alright, so I found one of them, I guess the train. So they want me to find the truck speed. But if I want to do that, all I have to do is say, what was the truck speed in that, up here? It was x plus 40, because that's the rate. So the truck was going x plus 40 miles an hour. That's all I really need to do is plug that in. So let me see. The speed of the truck, oops, speed of the truck was x plus 40. And now that I know x is 30, I can put that there. 30 plus 40 is 70. Aha! So the truck was going at 70 miles an hour, and the train was going 30 miles an hour. It's probably good to sum that up. The train was going 30 miles per hour, and the truck was going 70 miles per hour. Alright. Whew, that was a lot of work. These are tough problems. Very tough. That's why no one likes these problems. Have you ever heard people complaining or making fun of those problems that are saying, what is it? Oh yeah, train 1 left the station at 5:32 p.m. going north-northwest. And then train 2 left the station at blah blah blah. Anyway, if you've heard people complain about those problems or make fun of them, and you can see why, because this is that type of problem here. But let's try one more, and then I think we'll get the hang of it, sort of. These are very tricky. Okay, let's see. Part B, they're saying the current in the lazy river. Is that a real river? Oh well, okay. The lazy river moves at a rate of 4 miles an hour. That might help to write. You don't have to write that down, but it kind of helps me. That's the rate of the current. 4 miles an hour. Okay. You know what? I think I'm going to waste a lot of room there. I'm going to write that up here. Rate of the current is 4 miles per hour. Oh, because I want to put my table there. Okay. Yeah, I know I'm going to have to create a table here. I might as well go for it. See, I feel like I didn't leave a lot of room in the last one. I might make it a little bigger. Alright. It'll be distance, rate, and time. And as I read this problem, I'll see what the two parts of the trip will be labeled. I don't know yet. It said, okay, Mickey's motorboat moves 6 miles upstream in the same time it takes for it to move 12 miles downstream. Okay, and then they want to know, what is the speed of the motorboat in still water? Well, it seems like the two parts of this trip, or the two kind of things they're talking about, is he went upstream and then he went downstream. I think that'll be it. One's upstream and one's downstream. Okay, let's see. Is there something I can just fill in right away? Because that's step 1. Well, they said the lazy river moves at a rate of 4 miles an hour. But you know what? That's kind of That'll help us eventually, but that's not really telling us anything because, okay, that's rate, but that's not the rate of his boat upstream. That's what'll go here. What'll go here in this box is how fast he's going in his boat upstream. But 4 miles an hour is how fast the current's going, not how fast his boat's going. I think that'll help us, but that's not exactly what we want. Same thing with downstream. When he's going downstream, that's helping him, right? I mean, the current's helping him go faster, but he's not going as fast as the current. He might be going faster or slower or whatever. So 4 miles an hour is not going to go anywhere in this table. It'll be part of it, but it won't be exactly the right speed. So that's not really helping yet. Let me move on. Mickey's motorboat moves 6 miles upstream. Oh, there it is. 6 miles is the distance upstream. In the same time that it takes for it to move 12 miles downstream. Okay, that must be how... And again, miles is distance, so it's in the distance column, 6 for upstream, 12 for downstream. Okay, we got that. So that's step 1. Step 2 is now they should give us some kind of relationship between either the rates or the times. Okay, well, let's see. I think this is actually where that 4 miles an hour will come in. And I think in this one, it's kind of weird, but what they asked for is what is the speed of his motorboat in still water? So since that's what they're asking for, I'm going to let x equal that. X is the speed of his motorboat in still water. Because when I fill in the rate here, the speed, or it's supposed to be the speed of his boat upstream. So upstream, it's going to be harder, right? He's going to be going a little slower than his boat can normally go because the current's going against him. So his rate upstream is going to be, okay, his normal speed is x, right? We said that's how fast his motorboat would go in still water, but the current's pushing against him at 4 miles an hour. So really he's going 4 miles an hour slower than he would in still water. Basically, yeah, 4 miles per hour slower than he would in still water. Yeah, that's pretty much how it works, right? If the current's moving against you, it's slowing you down by whatever its speed is. So that would be my rate upstream, x minus 4. And downstream's kind of similar, except downstream, you know, when you're going downstream, it's actually, the current's helping you, so you're really going, however fast the current's going, faster than you normally would. Because it's pushing on you, I guess, pushing your back. It'd be x plus 4. He's going 4 miles an hour faster than he would normally, and his normal speed is x, because that's his boat's speed in still water. Alright, that's very tricky, but if you see that, these problems always kind of work the same. You might see a lot of these guys, these current ones. If the river's going at a certain rate, then his speed won't be x, it'll be upstream, it'll be x minus that, and downstream it'll be x plus that. Because yeah, he's not going the same speed upstream and downstream, he's going different speeds. Alright, so we've done step 2. Now step 3 says, the last thing we're going to fill in, okay, it looks like we're missing time, huh? We have distance and rate. We need t for time. So remember, like in the last example we did, we take the distance equals rate times time formula and solve for t. Just whatever variable's left, you're solving for that variable. And this one, it's the same thing as the last time. We divide both sides by r. That'll mean time is distance over rate. There we go. So to fill in that final column, I'm going to use that formula. So this distance here, this time here, will be the distance upstream, which is 6, over the rate upstream, which is x minus 4. So 6 over x minus 4. The other time, this guy, it'll be the distance downstream, which is 12, over the rate downstream, which is x plus 4. Whew! Alright, so we filled everything in. Now, so the last step, they said that they should give us some kind of relationship between these two last things we filled in. So I gotta think about what is the relationship between the last things we filled in were the times. Okay. Let me see. What do they say in this problem? They say the current of the river moves at a rate of 4 miles an hour. Okay, that doesn't tell me anything about the times. Mickey's motorboat moves 6 miles upstream. Aha, here we go. In the same time that he goes downstream. So kind of like, I think that was the same relationship as in the last one, huh? Times are the same. So his time upstream is the same or equal to his time downstream. Okay, that means I should be able to take his time upstream, which was, where was that guy? This guy, 6 over x plus 4, and place that here, kind of replace where I put the words time upstream. So that's 6 over x minus 4 equals, alright, the time downstream, we had that guy, he was here, 12 over x plus 4. So I'll go ahead and replace that guy with 12 over x plus 4. And that's it. That's just seems like such a nice equation. I can't believe, well, all the hard work was the brainstorming getting there. It just looks so nice. But now I think I'm able to solve this guy. Okay. The color's kind of weirding me out. I'm going to get rid of it. 6 over x minus 4, 12 over x plus 4. So I got to figure out, like we did in the previous section, what's the LCD here? Well, neither of these denominators factor, so my least common denominator is going to need either of those factors, x minus 4 and x plus 4. I'm going to need both, and I'm going to have to distribute both onto either term on the other side. I'm going to write that LCD x minus 4, x plus 4 next to the left fraction and next to the right fraction, because it's being distributed onto both. So it's multiplied by the left fraction, which is 6 over x minus 4. It's multiplied by the right fraction, which is 12 over x plus 4. Alright, let's see. I'm going to put either of those over 1 so I can see what cancels. So here, x minus 4 is cancelled to leave the 6 that was in the numerator times the x plus 4 that was part of the LCD that did not cancel. And then for the other one, I see that the x plus 4 is cancelled here. So the 12 that was in the numerator is left to be multiplied by the x minus 4 that was left in the numerator from the LCD. And I still can't believe how simple this is now. Now I just have to distribute that 6 in here, and then distribute this 12 in here. So we got 6 times x, I could do that, 6 times 4, and then 12 times x, and 12 times negative 4. Man, and now I realize I don't have to factor this. This is nice. I just have to kind of isolate x here. So I'm going to move the 6x over to the right. It's just kind of nice. I always move the smaller coefficient to the larger, you know? If I move the 6x over, the coefficient I end up with is positive, which is nice. Alright, now once I do that, 24 equals, that would end up being 6x minus 48. Now I want to move the 48 over to try to isolate x, so I'll add it. 24 and 48 is 72. And 6x is all by himself, and we'll be done if we just divide both sides by 6. There we go. Perfect. Let me see. 6 goes into 72 12 times, I believe. And I remember up there we made x equal to the speed of the boat in still water, right? I think we wrote that right. Oh, sorry. We wrote that directly next to the problem right here. The speed of his boat in still water. And that's exactly what they asked for. What is the speed of his boat in still water? So that's really all we need. We don't need to go find something else. So I'm going to say that the speed of his boat in still water is 12 miles per hour. Whew, that's a lot of work. So look at that. We only did 4 examples in 43 minutes. That's crazy, right? But don't worry. I don't want you to get worried and say, oh my gosh, that's how long it's going to take me. 4 problems in 43 minutes? Oh my gosh. No, but along the way, you won't have to be explaining what you're doing to someone. I think that's, what would take us a while, as I keep stopping and explaining it. But as long as you understand it, you're not having to explain it to someone, so you can keep going and not have to slow down, So it won't take you as long, don't worry, but be really careful. If you get stuck, just look back at these examples and try to model your problems after them, and maybe it'll be similar. But if you didn't like this chapter, don't worry, it's all over now. So we'll start a new chapter, which is a lot nicer. I think you'll like it. Very simple, especially compared to these examples. Each of these examples takes, 10 minutes or something. The examples we're going to see will take not even that long, not even close, maybe 10 seconds each. So it's a nice change of pace. But thank you for being patient. I'll see you in the next video where you get to start a new chapter in your lives.